Hello everyone, this is me, Ahmed Al-Garhi. I will be moderating this session today for Dr. Yasser Elshayeb. It is a great honor and pleasure to introduce Dr. Yasser, not only because he is one of the big names in rock mechanics and developing the, improving the education in Egypt and the, Middle East, but also because he was my favorite professor when I was doing my undergrad in Cairo University, and he was my supervisor also in in my final project, and he is the one who introduced me to the oil and gas. So otherwise, if I did not meet him, I should be doing mining engineering, not petroleum engineering. So thank you, Dr. Yasser. I will not talk much about yourself because I know you have a slide to talk about your education and achievements. So please, floor is yours.
Thank you very much. Good afternoon or good evening, good morning. I don't know at which time zone you are situated in. Thank you, Dr. Ahmed, for this kind invitation, and thank you, Dr. Ahmed, as well for this kind introduction as well. Indeed, you were at some point of time, I was your professor, but then we became colleagues, and I think we even worked together for a small period of time afterwards. And actually, I don't remember that I was the one who introduced you to oil and gas, but well, I'm happy that I did something good for you.
It is true.
Thank you so much. I'm happy to have 627 people now in the webinar room, and the number is increasing actually. So I'll start right away. I have a presentation here that I would like to share with everyone. So I'll just start, and as it says on the screen, the title is Rock Mechanics, and it's anecdotal actually because rock mechanics for me is something that is very important. It's my undergraduate graduation project as well. It's something that I would say goes in my veins, and I mean it works. And I mean I've been working in rock mechanics and in many aspects all of my life. And I was actually reading a paper like 2 or 3 weeks ago, and this paper said that rock mechanics is actually neglected by petroleum engineers. So I know that I'm getting into a troubled ground, but I hope that I will convince you with this presentation afterwards that it's worth it. I mean, you can benefit actually from rock mechanics as a petroleum or an oil and gas specialist or engineer or practitioner or whatever. Who am I? As Dr. Ahmed was saying, I'm Yasser Elshayeb. I had a BSc from Cairo University, Egypt in 1990 in mining engineering. And my graduation project was about actually rock mechanics, underground stress distribution, and some of the galleries in Egypt, in a coal mine in Egypt. Then in 95, I moved to France, where I had a pre-master, I would say, something, a diploma. I mean, in France, in French, we call it a diploma of studies of deep studies, or études approfondies. I don't know if you understand French, but anyway, it's a diploma of 1 year, similar to a master's, and it was about Monte Carlo simulation and statistical analysis, which introduced me to the world of statistics and simulation as well. Then back in Egypt in 1996, I finished my master's in Cairo University, and it was also on the same topic. I mean, I picked up the same topic from France, and I came back to Egypt with it, which was also Monte Carlo simulation and statistical analysis. Then back to France, I finished my PhD in 1999, and the subject of my thesis, I mean, was really multidisciplinary at that time. At that time, we were not very much acquainted with multidisciplinary PhDs, but I mean, maybe they were testing the ground with myself. So I was the testing bed. So it was about risk assessment, it was about geotechnical engineering, it was about fuzzy logic, it was about decision support systems, and it was also about GIS and statistical analysis. So it's a combination of many things. Then when I came back to Egypt in 2002, I started teaching my favorite subject, which is rock mechanics at Cairo University. And I continued since then with some years off here and there doing other stuff. I'm a member of the ISRM, which is the International Society of Rock Mechanics, because there is an international society for the people who are working on the rock mechanics. Actually, many of the slides that I'm using here are actually products of that society, and I have to give them credit for that. Of course, throughout the years, I developed a lot of research papers and in journals or in conferences about rock mechanics and application in various fields. And in actually, it was 2017, not 2007. I'm sorry for the mistake. I'll correct it afterwards. I had the grade of a professor of, as it says in my papers, rock engineering applications in heritage and archaeology, which says a lot about multidisciplinary aspects that I use rock mechanics in. So it's not only about mining engineering or petroleum engineering, but also it actually is in many aspects of life, and one of them is my favorite subject, or second favorite subject, which is heritage and archaeology. Now that's all about myself. Now the plan of this presentation, I'll start by an introduction. Why do we do rock mechanics? Why do we have to know some aspects of rock mechanics? Of course, we will not go into deep, but why do we need to know anything about rock mechanics? Why is it important for a petroleum engineer? What is the dilemma that we are living in rock mechanics since many years, and the main problems that we try to solve? Then I'll move on into some technical aspects of rock mechanics. I'll speak about stress and strain. And those of you who have studied maybe strength of materials or mechanical engineering, they may know what's stress and strain. But here we'll tackle it from a different angle of rocks, of natural material like iron or metal or even concrete. So we're speaking about different material, and it has to be a different aspect of dealing with the same topics, which are stress and strain. So we will speak about the tensors, stress in 2D and 3D and other stuff and whatever. Then a very important topic actually specifically for petroleum engineers is the in situ stress. And the in situ stress is very important, as I will show, and how to calculate it, how to consider it, how to know it exists, how to know its values, how to estimate its values. This is very important for you as a petroleum engineers, and of course for us as well as mining engineers. I mean, we use it all the time, but it is really an important topic that we need to consider. I'll speak briefly afterwards about the Mohr circle, which is a way to represent a geometrical way to represent stress and strain and deformation, whatever. And finally, I will end by two important topics, but not much time will spend on it, which is stress and strain. What's the relationship between stress and strain, which is the theory of elasticity and the constants, and the failure. How do we calculate failure in our work? And of course, this will be related to the first part of the presentation about the rock mechanics problem. So I will speak about the failure here, and then I'll speak about the failure afterwards, how to analyze the failure and so on. I have, I think 31 slides or 32 slides, which makes me speak about 45 minutes. And then of course, at the end, I guess Dr. Ahmed has planned it this way. There will be a phase of questions and Q&A, questions and answers, and I'll be, of course, happy to answer any questions that you'd like to ask afterwards. Now, let's start right away. Why rock mechanics? Because we live on a planet called Earth, and this planet called Earth is composed actually of rocks. And those rocks has been on the ground since many years, since the creation of the Earth, the creation of the Earth. The Earth, as you may know, or you may have read about it, was very hot at the beginning, and then started cooling down. and then life started appearing on Earth. And when I speak about life, I'm not speaking about us as a human being, but I'm speaking about other species like bacteria, like unicell, like anything else, like plants as well. And this is what we call today the magma, the lava, which is the very hot core of the Earth. And this constitute actually a type of rock that we deal with, that we use every day. Sometimes we use it for building as a building material. Sometimes we use it in order to penetrate it to reach for the underground, which is called the igneous rock. Then this igneous rock is decomposed and resedimented somewhere else through a physical process that we call weathering. And once it is sedimented, it becomes soil, and this soil is compacted and it becomes sedimentary rock, which is the second type of rocks that we have on the Earth's surface. Then comes other processes that happens on the Earth, because the Earth is always moving, is always on the move. There are things that are happening every day and every night. And there comes another type of rock, which you call the metamorphic rock, which is it is a derivative of the igneous rock and the sedimentary rock. And you will realize from this graph that I'm putting here on the screen that those processes those processes that I spoke about are not one-way processes. I mean, it's not magma that it go into igneous rock and then sedimentary and then and then soil and then sedimentary rock and then metamorphic rock. There are cases, or it happens, of course, all the time, that those types of rocks are interchanged. I mean, a sedimentary rock will become igneous rock after some processes, and igneous rock will become metamorphic rock, and metamorphic rock will become sedimentary will become metamorphic, whatever. I mean, those three types of rocks, sometimes we draw it in the form of a triangle, three corners of a triangle. And in order to say that those are, I mean, there are processes that will transform every type of rock to the other one. And all of those processes are driven by nature. Those are not or let's say man-made processes. The process of melting, the process of weathering, the process of transportation, the process of lithification, the process of metamorphism is always driven by nature. It's not a man-made at all. And that's why I always say that the rock is a natural material. It's not a man-made material, which makes a huge difference, big difference between a piece of metal or a piece of plastic that we get in our hand and the rock. So we're speaking, I mean, two different things. Some materials are natural, some materials are man-made, and this makes a lot of difference. Now, why do we use rock mechanics? Because we are actually exposed to these types of rocks. I mean, I have here some pictures of rocks, and of course, you all know. I mean, you all have been to the beach. You all have been to places like the picture maybe on the right-hand side or on the left-hand side, where you see rocks, and those rocks are naturally composed, are laid there, and they have like cracks in them. And we as humans, we need to deal with that medium. We need to deal with that with that material in order to work with it. And I'll speak about working with it. So here, for example, we are constructing roads and at the toes of some of the cliffs that we have. So, and we see the rocks while we pass on those roads. Even throughout ancient times, and even modern times, and of course, I have to be biased towards Egypt, my lovely country. In Egypt, since like 4,000 or 5,000 years ago, people started using those rocks to construct buildings. And still today, I mean, until today, we are still using some of the granite, some of the marbles in order to put them in the buildings that we are using. But this is just to say that in ancient times, all of the buildings were made out of this natural material called rock. with whatever its composition. Is it sandstone or limestone or granite or marble, whatever? But then the fact is that we always use this rock as a material for building, and this is again another reason why we need to study the mechanics of that material in order to understand it, in order to know how to deal with it afterwards. Now, those just a few examples of engineering works. So rock mechanics are very important for foundation design when we do foundations for whatever, for dams, for buildings, for whatever we do, for slopes like when we build roads, for tunnels and caverns. And I, as a mining engineer, I work a lot with tunnels and caverns, of course, with mining, and comes comes then waste disposal. I mean, in many places of this world, we are now storing the nuclear waste below the ground in very deep 200 meters or 300 meters rooms below the ground surface. We store the nuclear waste there, hoping that with time it will decay and it will be converted into MPB. I don't remember now. Into lead. Yeah, it will be converted into lead, and it will not be radioactive. And of course, the final work is petroleum engineering, and I put it here with geothermal energy as well, because this is a process that we know since, I would say, 200 years now, that people started digging wells in the ground in order to extract, at some point of time, water. But then we discovered that there is this very precious material that is below the Earth's ground that is called oil, another precious material that is below the Earth's ground that is called gas. And we are pumping and we are draining this ground in order to know how to extract this material that is below the Earth's surface. Of course, I'm speaking here also about the geothermal energy, because this is something that is booming actually in the world today, where you pump water in the underground, and you use the heat that is generated naturally by the Earth in order to heat this water and create vapor. And this is a process that is very, very, very similar to what is done actually in the oil and gas industry. The water injection process that we use in the oil and gas. So it's very similar process to it. Just to say that this is something that we also use in that we also need rock mechanics to work on. Now, this is the paper that I told you about. It's by Nathan Meehan in 1994. Yeah, in 1994. And the title of the paper is Rock Mechanics Issues in Petroleum Engineering. And it says in the abstract, historically, petroleum engineers have neglected the role of physical porous medium for its storage properties and its delivery capabilities. Engineers charged with maximizing hydrocarbon recovery address rock mechanics issue only of dire necessity, and then with little enthusiasm. So, I mean, it continues actually. Rock stresses what are the needs for rock mechanics in petroleum engineering, and this paper tries to pave the way, let's say, to put a benchmark to say that it is very important to use to learn and to understand rock mechanics as a petroleum engineer. And here I'm citing actually some of the outputs of this paper, and some of course of the experience that we know about why you as a petroleum engineer, you need to understand rock mechanics. And of course, when you do drilling in the underground, you need to understand rock mechanics. You need to understand the mechanics of the material that you are penetrating. So it's a clear case for drilling engineers. It can determine actually the drilling rate, whether you're in an igneous rock or a metamorphic rock, or what are the layers that you have below the surface. We use a lot. We always use rock mechanics when it's about hydraulic fracturing, And this is also very important for petroleum engineers and non-petroleum engineers. Now, well simulation, sand control, reservoir simulation. I mean, all of those aspects are very, very important and very relevant to the rock mechanics. Yeah. Now, the dilemma of rock mechanics, and this is one of the major differences that I have to stress upon when we speak about, as I said at the beginning, if any of you have studied strength of materials or mechanical engineering, you've knew stress and strain and elongation, and you've maybe had the chance to go into a laboratory and get a piece of metal, and then we make a tension test on it, and then this metal will crack, and we always do this. The dilemma of rock mechanics is that this natural material that we are working on is actually heterogeneous. It's not homogeneous at all. Even though we say that this is an igneous rock, even though we say that this is a metamorphic rock, or this is a sandstone, or this is a limestone, when we look into the chemical composition of those rocks, you will find that whenever you move like 10 centimeters from one place to another, the chemical composition of the material changes, and it changes a lot. So it is a heterogeneous material. It is also a discontinuous material. It's not a continuous medium. It's full of discontinuities, cracks, joints, faults. I mean, a lot of those those impurities, if you can call it this way, exist in this medium that we call rock. And the third characteristic that is also in rocks is that it is anisotropic. And anisotropic means that it's like wood. When you get a piece of rock, if you will compress it in the z-axis, it will give you a different strength than if you will compress it in the x or y axis. And this is again a big difference from metal, for example. I mean, if you have a piece of metal, whether you will stress it vertically or horizontally, it will give you the same properties. But in rocks, it is usually not. And here I'm putting some drawings about sources of those impurities, heterogeneity, discontinuity, and isotropism that are here in this in those graphs. Why is it heterogeneous? Why is it discontinuous? Why is it anisotropic? It's because of the Earth's surface. It's because of the movement of the Earth. It's because of the pressure or the stress. I will speak about the stress afterwards. That is that this rock is subjected to. And over and above, not only heterogeneous, anisotropic, and discontinuous, but it is also subject to water. And when the water comes to penetrate inside the rock, it also changes its properties a lot. I mean, it has good effect, it has bad effect on what we consider good and bad, but humidity changes the way the rock behaves. So it is also something that we need to consider. And finally, we have a lot of in situ stresses that I'll speak about in details afterwards that are existing with the Earth. So if you are, for example, now you want to drill a hole into the Earth's crust in order to reach out for an oil trap or an oil reservoir that is like 1,000 meters below the surface, you need to understand what are the pre-existing situation of this rock 1,000 meters below the ground, and how can you do that, and what are the layers that you will penetrate, and what is the rate of penetration of those layers. All of those things you need to before starting to drill your hole or your well. Now, generally speaking, very macro level, what is the problem? The main problem of rock mechanics and engineering. And I would say it's quite similar to those of us who work in civil engineering. I mean, you need to build something, or you need to dig something, you need to do an engineering work, and the material that you're working with has a certain strength or a certain resistance. And you need to know if this excavation, if this thing that you will build or that you will dig will be stable or not. So you need to understand the forces that are acting on it, and you need to understand the resistance that is acting on it as well. And you need to maybe to have a factor of safety to make it stable. So if you are digging an oil well, and this oil well will be 1,000 meters below the ground, you need to know this oil well, what is the resistance of the rocks that you will be penetrating, and what is the pressure or the stress that you will be applying on those rocks, and the difference between the two, actually the ratio between the two, the force and the resistance, is the failure probability, I would say, or the failure possibility, I would say. So that's why you need to understand. And this is, I would say, this is everything in engineering. I mean, if you're a mechanical engineer and you want to design a car, then you need to make sure that the resistance of the material that you are putting into the car will resist all these stresses, air, vibration, whatever it will go on the road. So, I mean, here in petroleum engineering, when we deal with rock, we also do almost the same thing. So we need to know what's the status of stress and what are the forces and what is the resistance that is there. What is, of course, all the boundary conditions that are there, like the water flow, the forces that are applicable and everything, in order to understand how this rock will behave and if it will fail or not. If it will not fail, then very good, then we can go on and continue. If it will fail, then we need to find a solution for it, and it becomes an engineering problem. Okay. Yeah, I mean, again, I think here I'm just repeating the same thing that I've just said. What are the forces applied? What are the elements of resistance? How safe is the structure, be it an underground excavation like the ones that we do in mining engineering, or be it just a borehole or just an oil well that of 4, 5, 10, 15 inches that we are putting in the ground. Now let's speak about stress and strain. And actually, I'll speak more about stress, because strain is the result, but stress is the main driving force. And the basic concept is that stress is a tensor, and tensor is a mathematical term that denotes, that gives some meaning. And here I'm starting in vector mathematics. In vector mathematics, we say that we have scalar quantities which are like temperature, like energy. Those are the quantities, those are the things that we measure that has only a value. So the temperature is 60 degrees Fahrenheit. That's all. I mean, there's nothing else to be said. 6 degrees. I mean, energy is 30 kilojoule. HP or 200 HP, for example. It's just a quantity. Then comes other phenomena, other physical phenomena that has a quantity and then has a direction. So it has a magnitude and it has a direction. And this is like the velocity. This is like the force, because a velocity, I mean, when you say or speed, when you say my speed is 300 kilometers per hour, need to say direction northeast, or direction east, or direction south, or whatever, or normal, or tangent, or whatever. Then comes a tensor, which actually it's a quantity that has a magnitude. It has also a direction, and it has a plane of application. And this is actually what stress is about. So when we speak about stress, we don't only speak about 400 megapascal. No, we speak about 400 megapascal. What's the direction, and what is the plane that this 400 megapascal is applying on. I always, in this presentation, you'll always find me putting here in dark blue a note called reading in italic. And I use this just to say that if you need to know more about this subject, of course, I mean, we don't have a lot of time here, but if you need to read more about this subject, then this is what you need to search about in Google, for example. So you need to look into vector and tensor mathematics. It will give you a lot of information about the things that I'm saying here. Normal and shear stress. We have also in physics a phenomena called, I mean, we know it, that a solid can sustain a shear force, whereas liquid or gas cannot. I mean, if you have a liquid or gas and you cannot do any shear on it, I mean, it's just a liquid, it's just a fluid that is there. And liquid and gas contains pressure. I mean, it endures pressure. While rocks can sustain shear force, and it can contain stress, which is actually a tensor quantity. So this is again another difference between if we consider, for example, oil and gas, or the oil itself, and the rock that is containing that oil. So the oil, we can measure its pressure, we can measure the pressure of that oil. But if we speak about the rocks, we need to speak about stress, we need to speak about the direction of application, and we need to speak about also the plane of application. Again, the reading here will be normal and shear stress in solid and fluids. Now, the basic concept, and maybe you've heard about it before, the stress by definition, if we speak about 2D, is the force per unit area. So we have a 2D plane, and in this 2D plane, you have a force that is applying on it, and this force is applying with, I mean, this is the plane of application here. So when you apply this force, you have the F, you have the direction, and then you have the plane of application. So that we're constructing the tensor actually now. And here we start speaking about normal force and shear force, which is translated into rock mechanics, because we divide this by the unit area, because the force itself is not important. What's important is the ratio between the force and the unit area, which we will call the stress. So the stress, we have the normal stress, the sigma n, and we have the shear stress, which we denoted by the Greek letter tau. And we have the angle of application, which is theta, that we have here. And those are usually the three symbols that we will use all over. I mean, sigma for stress, tau for shear, for normal, tau for shear, and theta for angle of application. Sometimes we say sigma n and sigma t, which is, sigma s, which is sigma normal, and sigma shear, sigma s. But this is, I mean, it depends on the place that we are working. Now, if we put this into in the form of a tensor, then in 2D we have sigma x, we have sigma y, and then we have the tau xy. This is the composition of the force in 2D. Mathematically speaking, the normal is the sigma multiplied by cosine theta, and the shear is the sigma multiplied by the sine of theta, and that's it. Now, if we move into 3D, it becomes a little bit more complicated, because we have 3 surfaces. Actually, we have 6 surfaces in a cube, but I will speak about the symmetry right after now. On every plane of the cube, we have a sigma x, we have a sigma y, and we have a tau xy. And in order to make things easier, now we start using xx, xy, xx, yy, and zz to say that this is on plane x, this is on plane y, this is on plane z, which is then analyzed or factorized into sigma xy, sigma and tau xy, and so on. So for every for every plane, you have the normal and you have two shears. You have one in this direction and you have two in the two other directions. And if we look into it in a tensor format, you have the sigma xx, sigma yy, and sigma zz, and then you have the tau xy, the tau xz, and the tau yz, and those are the ones that are actually here we speak about the sigma x in the direction of y, sigma x in the direction of z, and here we speak about the sigma y in the direction of z, and so on. Now this is, if we are speaking about a cube, a big cube, where we have 6 surfaces, so we should have 9 components, as it's written here, 9 components of stress. But actually what happens is that usually when we speak about stress in 3D, we speak about the symmetry of the values, because usually the sigma or the tau xz is equal to the tau that is resultant of the sigma z in the direction of x. So this value and this value are the same. This value and this value are the same. This value and this value are actually the same, which makes us believe or say that usually a stress tensor in 3D, it has only 6 components. It has only, maybe we can write it, it has only those, I don't know if I can do this, pen, yes. It's only those values. I mean, the 3 others, we can neglect them because the 3 others are actually are redundant, are symmetrical to the ones that are and this makes our life much easier. So instead of calculating 9 values, we need to calculate only 6 out of them, and that's it. The same thing happens for 2D, stress in 2D. So we, instead of calculating 4 components, we calculate only 3, because we know that tau xy is equal to tau yx. And even though I write it here as tau xy and tau xy, I should have written it tau yx, but it's the same. So the values are the same, and that's why we don't do that. Now let me move to the next. Yeah, this is what I just said about the symmetry of the tensor, and that's why we don't consider the values below the diagonal. We just consider the values above the diagonal, and that's it. So we have only 6 independent components, and that's it. Now, one of the of course, there is a lot of mathematics here, a lot of mathematics in how to calculate those stresses and so on. And throughout the years, scientists have discovered actually some interesting observations mathematically, and those interesting observations are materialized into this into those 3 equations. Don't be intimidated by the equations. I know that they look very complicated, but we call those the stress invariants. And stress invariants, it means that those are values that we can actually calculate, and they are constants. So for every situation, if you have an x, sigma x and sigma y and sigma z, and you add sigma x and sigma y and sigma z, it will be always equivalent if you add other x and y and z. Because if you have a cube, and this cube is in space, and you have a stress applying on it, then you have a certain sigma x and sigma y and sigma z. If you rotate this cube into space, and you still have the same stress applying to it, then you will find a different sigma x and different sigma y and different sigma z. But the fact is, if you will add those 3 components together, you will find always the same value. And it goes again for the 2nd order, it goes again for the 3rd order of calculations. Those are just calculations. It helps us sometimes to deduct the value of sigma, one of the sigmas, out of the other sigmas. So it's very important, and it's very interesting mathematically for those who are working in rock mechanics. Now, another interesting fact is that principal stresses. This is a concept that has been developed also by mathematicians and rock mechanics and mechanics of materials. And principal stresses are the stresses where you, I mean, it's the position in space. As I was just saying, you have a cube, and this cube is subject to an amount of stress. Then if you will rotate this cube on the x-axis or the y-axis or the z-axis, you will have a different amount of stress. But then we have observed that there comes a situation when you rotate this cube into space, you will find that there are only normal stresses applied to it. So you have only sigma x, you have only sigma y, and you have only sigma z, and you don't have any shear stresses applied to it. This is a very unique situation. It happens only once. And this is what we call the principal stresses. So it is, I mean, the principal stresses by definition are the values of three stresses applying on in 3D, applying on a cube, on a very small cube actually, and those three components of stress have no shear. They are only normal stress. And here I have the cube, and the cube is turned into space, is rotated into space, and then you have sigma 1 and sigma 2. We usually call it sigma 1 and sigma 2 and sigma 3. Sigma 1 to say that this is the maximum stress, this is the normal stress, the maximum, and this is 2 and 3. And usually, in many cases, 2 and 3 are more or less the same value. This is what invited us actually to represent principal stresses by this ellipsoid. So you have here sigma 1 on the x-axis, or we can call it x or y or z, whatever we call it. So we call it sigma 1, and then you have sigma 2 and you have sigma 3. And as I said just before now, sigma 2 and sigma 3 are usually the same. Their values are the same. So usually we calculate sigma 1 and sigma 2, and then we know that sigma 3 is the same value as sigma 2. So this is also important. Another very important aspect is that all free surfaces are principal stress directions. Because if you have a free surface, if you walk in the nature and you find a cliff, and this cliff is naked to the sun, this means that there is no stress applying on it. So this means that maybe this is the minimum stress, and it is a principal stress because there is no shear as well. And this is what's presented here in this graph on the right hand side below. It says that at point A there might be two directions of principal stresses. In point B, those directions are rotated somehow. But then when it comes to point C, you will find that there is always a normal and a shear stress that is parallel to the opening. And this is also very important for us because it makes us understand and know the directions of the principal stress, because it's important to know. Now, the readings that I'm putting here is stress rotation. Maybe you need to read about stress rotation, how to rotate it. And I'm putting here the equation that we use in order to deduct the maximum and the minimum stress in 2D out of sigma xx and sigma y and tau xy or sigma xy. We usually use sigma and tau as two symbols for the same thing. And this is this would be the angle of inclination of the principal stresses with respect to the direction of sigma x and sigma y. Now, I'll try to move a bit faster because I realize that time is running. Usually, when we work on the underground, we have circles like this. I mean, we have stress distribution. We call it stress distribution like this. So you can imagine that this is the hole that you are digging in the ground, and this is a horizontal cross section, and those are the stresses that are applying to your well or to your oil well, for example. You need to know those stresses in order to put some support for this oil well in order not to collapse, for example. We use this as well in tunnels in order to put support in order for the tunnel not to collapse. So we use it maybe horizontal when we do horizontal tunneling, but as a petroleum engineer, you may want to use it also vertically because you have your wells going vertically. So it's the same. Now I'll come rapidly to the in situ stress, and I'll speak about in situ stress. And in situ stress is actually the result of everything that happened on Earth since its creation until today. So I'm going into the desert, and in the desert I would like to dig a hole into the ground in order to search for water, or in order to search for oil or for gas, because I was told that there is some oil and gas here. Now I need to know what happened to this area before, what happened to this area since 400 million years ago, because this history of this Earth will make me understand the in situ, the pre-existing state of stress, or what we call in rock mechanics, the in situ stress. And here I'm including a lot of reasons for this in situ stress. So of course, gravity, because the Earth is layers above each other. Then we have tectonic stresses coming from active tectonics, earthquakes, faults, whatever. Some residual stresses that happen from magma cooling or from previous movement in this area. And then terrestrial stresses. Of course, you all know about the theory of plate tectonics, where all the continents are like floating on a sea of magma, and those tectonics are moving and are colliding with each other, and those collisions, it induces a lot of stresses, a lot of storage of stresses in the ground. And this is one source as well of in situ stress that we need to take into consideration. This is a graph, two graphs actually, about two places in eastern and western Australia, and people around many years have actually measured the underground stress that you can find in the ground. And let me here stop and say one thing. If you have a liquid, and this liquid is like 3 meters high, and you need to know the pressure of this liquid at the bottom, the equation to know that is simple, very straightforward. It's gamma, which is specific gravity of the fluid, multiplied by the H that you have. This is the equation that we use in dams. This is the equation that we use in water tanks. This is the equation that we use even in submarines. This is the equation that we use when we do scuba diving. I mean, it's everywhere. You multiply the specific gravity, and you multiply it by the depth, and you get the amount of pressure that will be applied on you when you are in this place or on this place. And usually this application of pressure is in every direction. And I recall what I said before, that this happens in fluids, but when it comes to rocks, when it comes to solids, it's a completely different story. Now, in order to calculate the amount of gravitational pressure or gravitational stress that is applicable when we reach out for 1,000 meters below the ground, where the surface is composed of sedimentary rocks and metamorphic rocks and igneous rocks and whatever, you cannot use the same equation. You cannot use the equation of gamma H. How can we calculate it? I mean, we have a lot of empirical equations, and one of them that I would like you maybe to retain to come out of this webinar is that when we speak about rocks at large depth, we speak about 0.028 H. So if you are digging a borehole, an oil well, and this oil well is expected to reach 1,000 meters below the ground, then if you want to know the stress, the vertical stress that will be applied in megapascal, you just multiply the 0.028 by the H, and you will get the empirically, you will get empirically the amount of stress that is there. And the source of this 0.028H, 0.028H is actually those points here. So we collect, we measure stresses underground, and then we put them on a graph like this, and then we do correlation or we do regression. So we can have a number like a line like this, and you maybe you will agree with me that the line would be like something like this. Now, if you want to know the equation of this line, that's the 0.028H that I was just speaking about. And I'm putting here those two graphs in order to say that, well, yes, empirically it's 0.028, but maybe in some areas we will find a different value. But in order to find this different value, we need to find to dig a lot of holes. We need to make a lot of calculations as well. Now I'll move on to Mohr circle, and I'm pretty sure that many of you have seen this, have seen those graphs before. And the Mohr circle is a way to represent graphically stress and normal and shear stress in the ground, or even in mechanics of materials. So if we take a circle like this, we have here the sigma 1, the sigma 1, we have here the sigma 2, which is the maximum and the minimum stress. And then we draw this circle where the center will be sigma 1 minus sigma 2 divided by 2. This is this distance will be sigma 1 plus sigma 2 divided by 2, while the radius of this circle will be sigma 1 minus sigma 2 divided by 2. This is the radius of that circle. And usually you have here the normal stress on the x-axis, and you have the shear stress on the y-axis. And the game that we play here is that if I will draw a line like this, it will tell me that this angle is 2 theta. So this this point tells me that if you have your stress applied on an angle of theta, where I have here 2 theta, you can expect this amount of normal stress, and you can expect this amount of shear stress here. So it's a way to see how can we represent normal and shear stress, and what's are the relationship between them. And when normal stress is decreased, shear stress is increased, and so on and so forth. So it is a way to represent it. And again, I'm sure that you may have seen this way of graphics before, and you may also want to look into Google and type Mohr circle for stress analysis or stress understanding, and you will get a lot of materials and a lot of information. Another aspect that we also find in the underground, I'm sorry, this slide should have been maybe in the in situ stress. It's misplaced here. Is that whenever we go below the Earth's surface, we observe an increase of temperature. So you go into the ground, and you will have a mechanical stress, which is resultant of many things, but also you will have a lot of thermal stresses. And here we are speaking about this thermals, how much this, again, empirically speaking, how much temperature is increased whenever you go below the Earth's surface. And I will invite you here to read a little bit about this coupling. We call it the thermal, hydrological, mechanical coupling, because this rock that is below the Earth's surface is subject not only to mechanical stress, but it's also subject to hydrological stress from water or from oil or from gas. And it's also subject to thermal stress resulting from it being below the Earth's surface. And you will find from this graph that you can derive an empirical formula that would tell you for in the first 1,000 kilometers below the Earth's surface, how much temperature will be increased, shall I find? Because this has a lot of implications on, for example, if you are drilling using an iron pit, and this iron, and you are drilling a hole that will go something like 1,000 kilometers. I know that it's very long, but it never happened before, I think. But if you will go for 1,000 kilometers, you may expect that the heat, the amount of heat that is that you will be drilling your hole in it, will maybe cause other troubles other than only the mechanical stress that is applying on your waterway. Now, the final two parts of the presentation, and again, you may have seen this this graph before. It's the stress strain curve, where we put our specimen under a machine, and we start to measure its strain caused by the stress applied. Usually in strength of material, you have a graph that is like this. I mean, you speak about iron, for example, you have a graph that is like this. And then I mean, the specimen will collapse. But in rock mechanics, it usually takes more time to, or the curve is usually, I mean, much longer, I would say, because again, of the nature of the rock that we are that we are working with. We in the first part, where it's more or less linear, so more stress, more strain, we call it the elastic region. And then it comes a zone where things are, I would say, completely out of control. So not much stress, but very much more strain, and then it will go up, and then it will collapse here. I mean, and of course, I mean, if you look into the literature, you will find a lot of research that is still being done on the values and the behavior in this area or in this area here, or whatever. But generally speaking, this is the curve that we speak about when we speak about rock mechanics, stress and strain relationship. And of course, I mean, if we speak about stress and strain, then we need maybe to start defining some values, some constants. And the most important is the Young's modulus, which is the ratio between stress and strain. So you measure the stress applied, you measure the strain that is resulting from that stress, and you divide those values by 2, and you get a modulus called Young's modulus. We call it even the Young's modulus of elasticity. We have another modulus another constant that we use, which is called bulk modulus, which is the stress divided by the ratio of stress divided by the volumetric strain, so the change in the volume when we do compression. Then we have also rigidity modulus, which is the shear stress divided by the shear strain. That's also quite important. Then we have an interesting ratio, which is, we call it the Poisson ratio. And this Poisson ratio is the lateral strain divided by the longitudinal strain. So you divide, I mean, you stress a piece of rock, and then you measure the lateral strain that happens and the longitudinal strain that is also happening. And the ratio between those two is Poisson ratio. And you can, of course, start asking questions about the limits of that value. Can Poisson ratio, can we have a lateral strain that is, sorry, can we have a longitudinal strain that is equal to lateral strain? Can this happen, that you have lateral strain that is the same as the longitudinal strain? Can this happen? Can this ratio be, for example, of a value of 1? I mean, those are very good questions that we can ask, and we can answer answer them mathematically. And actually, the relationship, I mean, there is a mathematical relationship between all those 4 moduluses that you can find also in the literature. If you would type on Google relationship between elasticity constants, you will find that the bulk modulus could be computed as Young's modulus multiplied by X or Y or Z, and things like that. Yeah, I mean, this is the reading. It's a relationship between elastic constants. Maybe you need to look and to look at it. Yeah, final word, very rapidly. I know that time is running, and I'm sorry that it took me so much time. Is on failure. What makes it fail? And this is what we usually do. I mean, is we usually use Mohr circles. We draw the x-axis as the sigma, the normal stress. And so we have here a sigma c, which is compressive strength, the amount of compression that we have applied on our specimen. And then we have sigma t, which is the tension strength that we have applied on our specimen. And then we take the tangent of those two angles, of those two circles or half circles. And we define here two constants, a constant called phi, which we call it the angle of internal friction, and a value called cohesion, which is this value. And we use this a lot in order to the failure mechanism and the failure criteria of any rock. I can tell you, for example, that this phi, this angle phi, is the angle which, when you go to the beach and you sit on the sand and you start building cones of sand, this cone of sand, it cannot have an angle more than 43, 42 degrees. And this 42, 43 degrees is actually the angle phi, is the angle of internal friction. It's a physical property of the rock. So next time you go to the beach and you have some sands and you try to make some cones out of it, try to think that this angle of this cone that you will do with your sand is actually a physical property of that. It's a mechanical property of that rock, and you need to put it into in mind. Now there is a lot of research as well going on the failure mechanism. I think I had it at some point of time. Yeah, I think maybe I put it in the reading. It's in the reading here. I call it the failure criteria of rock, because you will find that there is a lot of research done on that. There are at least in the world today 4 big families of failure criteria, how the rock is failing and how to calculate, how to predict its failure. All of this is, I mean, you can find it very easily on Google if you search for failure criteria of rock. Now, a recap. Again, I'm sorry I ran out of time. In the introduction, we spoke about why rock mechanics for petroleum engineering, and we saw that it's very important for drilling, it's very important for reservoir analysis, for hydraulic fracturing as well. And we spoke about the dilemma that this is a natural material, and this natural material is heterogeneous, is anisotropic, is humid, is as well fractured, is not continuous. And the problem is to predict its stability. Now, stress, it's a tensor. It's not a scalar. It's not a vector. It's a tensor because it has also the plane that it's acting on it. We have stress in 2D and stress in 3D. We have normal stress and shear stress, and we can present it mathematically by a tensor. It looks like a matrix, but it's not a matrix. It's something different. Then we have the concept of principal stresses, which is a rotation in space where you have only normal stresses. You don't have any shear stresses in it. Then we spoke maybe sometime about the in situ stress and why is it there, and why we need to know it. And empirically, again, 0.028 multiplied by h, that's the empirical equation for in situ stress, vertical stress. Mohr circle, I didn't speak much, but I know that it's there. You can search for it on the internet. Then we spoke rapidly about the elasticity moduluses, Young's modulus, bulk modulus, Poisson ratio, and so on. And finally, the failure mechanism of rock. And here I invite you really to look into this reading, Rock Mechanics for Petroleum Engineering. You will find a lot of literature, papers and books on the internet that are speaking about, even presentation that are speaking about this concept, and you may want to have a look at it. Thank you so much. It's been a pleasure. Thank you so much, Dr. Ahmed, for inviting me here. Thank you so much for everyone who was here. I'm sorry for the time that has run from me. And of course, I'm ready for any questions that you may have.
Thank you, Dr. Yasser, for the great presentation. Before I start asking questions, just I want to announce something very quick. I received many questions, very technical and related to tools and and saying applications in oil and gas. And what I want to tell you, we have 4 more technical webinars about geomechanics applications in oil and gas. So it will be more relevant to keep these questions for these webinars. I will select only questions related to the material presented today, just to make it,
yeah. This presentation actually, as Dr. Ahmed is saying, I mean, the main purpose of this presentation is just to give you an introduction, about it. Now, definitely, if you want to go deep into geomechanics, it's a different world, and it's a different presentation, as he said.
Okay, sir. So the first question, as usual, are you willing to share your PDF or not?
Yes, of course. I mean, I'll just convert the PPT into PDF, and I'll send it to you. And of course, you can. I mean, I can share it with anyone.
Okay, thank you very much. The second question, I got a question about what is the difference between isotropic and anisotropic?
Isotropic is that isotropic material is a material where you have all the elastic constants are the same in all directions. So if you have a piece of metal and you will compress it, if you have a piece of metal like this, like the one that I'm holding in my hand, it's an envelope opener. So if you will press it in this direction, you will get a value, and if you will press it in the second direction, in the y value, in the y axis, you'll get the same value. So this is an isotropic material, while in rocks it is not. In rocks, if you will compress a piece of rock, I mean, it's like a book, it's like a glass, a piece of glass. So a piece of glass, if you'll compress it in this direction, it has a value, and if you compress it in the other direction, it has a completely different value, and we call this an isotropic.
Okay, so I got a question asking about the meaning of overburden, and maybe it will be nice to proceed and tell us something about maximum horizontal stress and minimum horizontal stress also.
Overburden is is what is above anything that interests us, i.e., I have my oil trap 1,200 meters below the ground. So this means that I have 1,200 meters of overburden. So it is what is above what I'm interested in. This is what usually what we speak about when we speak about overburden. It's a term that we use a lot in petroleum engineering, of course, and mining. I mean, in all civil engineering works, we use this term of overburden. Now, maximum horizontal stress and minimum horizontal stress. Those are values that you need to calculate according to your excavation, according to your in situ stress, and also according to your Poisson ratio that you need to calculate for your rock material. So it varies from one place to another.
Okay, so the last question I have for today, someone asking, is it any relation between the rock mechanics and wellbore stability? I believe it is.
Yeah, of course.
Easy one.
Of course.
Yes, the answer is yes.
Of course. Of course. Yes, yes. The answer is, of course, yes. Yes.
Okay, before we finish, one more time, we will have a webinar, another webinar about wellbore stability of deep water. We will have a webinar about mechanical earth modeling. We'll have 2 webinars about applications of geomechanics in oil and gas. So just wait if you have questions regarding the tools and what is exactly going on in oil and gas companies. Just wait, not too long, and you will get these webinars. Thank you, Dr. Yasser, and have a wonderful evening. Thank you, everyone, and have a wonderful evening and wonderful night. Thank you.
Thank you so much. Thank you so much. Thank you for giving me this opportunity. Thank you,
You
everyone.
are always welcome, sir.
Thank you. Bye-bye.
Bye.